Hello class, welcome to Stat 1200. I am your instructor William Buellman, and today we are covering section 8.2, hypothesis test for a population mean, sigma, the standard deviation, known. Our objectives for today are to perform hypothesis tests with the critical value method, perform hypothesis tests with the p-value method, describe the relationship between hypothesis test and confidence intervals, describe the relationship between alpha and the probability of error, report the p-value or the test statistic value, distinguish between statistical significance and practical significance. There are two ways to perform hypothesis tests. Both methods produce the same results. The methods are the critical value method, and the p-value method. In a hypothesis test, the idea is to select a sample, calculate a statistic such as x bar, the mean, and compare it to the value in the null hypothesis, h0. If the difference between the sample mean and the value in the null hypothesis is large, it is less likely to be due to chance, and the null hypothesis is less likely to be true. Otherwise, a small difference may be due to chance, and the null hypothesis may be true. We must determine how strong the disagreement is between the sample mean and the null hypothesis. Example 1. We begin with an example. The College Board reported in a recent year that the mean math SAT score was 515 with a standard deviation of 116. Results of an earlier study suggest that the coach students should have a mean SAT score of approximately 530. A teacher who runs an online coaching program thinks that students coached by his method have a higher mean score than this. Because the teacher believes that the mean score for his students is greater than 530, the null and hypothesis are as follows. The null is that the score is 530. The alternative is that it is greater than 530. Suppose now that the teacher draws a random sample of 100 students who are planning to take the SAT and enrolls them in the online coaching program. After completing the program, their sample mean SAT scores is 562. This is higher than the null hypothesis value of 530, but to determine how strong the disagreement is between the sample mean and the null hypothesis, we calculate the value of the test statistic, which is just the z-score of the sample mean. Assuming that the population standard deviation is 116, the test statistic of the sample mean x bar is 562 minus 530 over 116 divided by the square root of 100, which is equal to 2.76. Again, the test statistic is 2.76. Visually, we can see from the figure that I'm about to draw that based on our observations of x bar equaling 562, it is pretty far out in the tail of the distribution. So I'm going to go ahead and draw that right now. So we can see from the sketch that a z-score of 2.76 is pretty far to the right. So that's pretty far out there from the mean, which was 530. Intuitively, it appears that the evidence against the null hypothesis is very strong since we're so far away from the mean. The critical value method is based on the idea that we should reject the null hypothesis if the value of the test statistic is unusual when we assume the null hypothesis to be true. We choose a critical value, which forms a boundary between values that are considered unusual and values that are not. The region that contains the unusual values is called the critical region. If the value of the test statistic is in the critical region, then we reject the null hypothesis. So what this is saying is if a value is in that blue shaded region, it is in the critical region, and thus we reject the null hypothesis. The probability that we use to determine whether an event is unusual is called the significance level. The significance level is denoted by the letter alpha. Therefore, the area of the critical region is equal to alpha. The choice of alpha is determined by how strong we require the evidence against the null hypothesis to be in order to reject it. The smaller the value of alpha, the stronger the evidence we require. One of the most commonly used values for alpha is 0.05. When alpha equals 0.05 is used in a one-tailed test, the critical value is 1.645. Recall for the math SAT score example that the test statistic z was 2.76. Since z, which equals 2.76, falls in the critical region, we reject the null hypothesis at alpha equaling 0.05. We conclude that the mean SAT score for students completing the online coaching program is greater than 530. So we can see here down in our shaded region, that's where our z equaling 2.76 is, which is to the right of our critical value. So since it's in the shaded region, we reject the null hypothesis. The location of the critical region depends on whether the alternative is a left-tailed, right-tailed, or two-tailed. So for a left-tailed, the critical value is negative z alpha. So we're worried about the left-hand area. For the right-tailed, the critical value is positive z alpha. And for a two-tailed, you notice we have half of the area on the left and half of the area on the right. So for a left-tailed test, we reject the null if z is less than negative z alpha. For a right-tailed, we reject the null if z is greater than or equal to z alpha. And for a two-tailed, we reject the null if z is greater than or equal to z alpha by 2, or if z is less than or equal to negative z alpha by 2. So if our z value that we calculate is in those shaded rejection regions, we reject the null. The table indicates the critical values for some commonly used significance levels of alpha, which it doesn't seem to be here. I don't know why it's not showing up, but the common levels are usually 90, 95, and 99% as. So your alphas would correspond to 0.1, 0.05, and 0.01. The assumptions for performing a hypothesis test about mu when sigma is known, so about the mean when the standard deviation is known, are that we have a simple random sample and that the sample is large, so greater than 30, or the population is approximately symmetric. So let's do some examples. Example 2. The American Automobile Association reported that the mean price for a gallon of regular grade gasoline in the city of Los Angeles in July 2013 was $4.04. A recently taken simple random sample of 50 gas stations in Los Angeles had an average price of $3.99. Assume that the standard deviation of the prices was 15 cents. An economist is interested in determining whether the mean price is less than the $4.04. Use the critical valued method to perform a hypothesis test at alpha equaling 0.05 level of significance. We first check our assumptions. Simple random sample, check. Is the sample size greater than 30? It is, check. So the assumptions are met. Null and alternative hypothesis are, so the null is mu is equal to the $4.04. The alternative is mu is less than $4.04. So that is our null and alternative hypothesis. The significance level was given as alpha equaling 0.05. Since it's less than, this is a left-tailed test. So we look at this table right here, and we see at 0.05 for a left-tailed test circled here, the critical value is negative 1.645. So now we're going to compute the test statistic and compare it to the critical value. So here's the test statistic. So 3.99 minus 4.04 over 0.15 divided by the square root of 50, which gives us negative 2.36. This is a left-held test. So we reject the null hypothesis if z is less than negative 1.645, since negative 2.36 is less than negative 1.645. We reject the null hypothesis at alpha equaling 0.05. We conclude that the mean price of a gallon of gasoline in Los Angeles is less than $4.04. The p-value is the probability that a number drawn from the distribution of the sample mean would be as extreme as or more extreme than our observed value of x bar, the sample mean. Unlike the critical value, the p-value tells us exactly how unusual the test statistic is. For this reason, the p-value method is more often used in practice, especially when technology is used to conduct a hypothesis test. The smaller the p-value, the stronger the evidence is against H0. So a smaller p-value shows more evidence against the null hypothesis. So again, we have the same coach where he claims that his coaching increases the student scores. So the sample mean, again, as a reminder, was 562. So suppose that the population standard deviation was 116. Do we have strong evidence against the null hypothesis? So we're going to begin by assuming that the null is true. Therefore, we assume that the mean of the sample should be 530. Since the sample size is large, we know that x bar is going to be approximately normal with a standard deviation of sigma over the square root of n, which is 116 divided by the square root of 100, which is 11.6. So we calculate the test statistic, which we've already done this, and we got 2.76. Visually, we can see from the figure that this is far away. So we've already done all this. This is just a recap of what we've shown before. These figures are nothing new. They're the same figures as before. And again, intuitively, the evidence against the null hypothesis is very strong because we're very far away from the value that we think it should be. The p-value is the area under the normal curve to the right of the z value that we found. This area is equal to 0.0029 using table A2. Therefore, the p-value for this test is 0.0029. The p-value is the area under the curve to the right of the z-score of 2.76. Such a small p-value strongly suggests that the null hypothesis should be rejected. So remember, smaller p-values show more evidence against the null hypothesis. We have seen that the smaller the p-value, the stronger the evidence against the null hypothesis. Therefore, to make a decision to reject the null hypothesis when using the p-value method, we choose a significance of alpha between 0 and 1, and we do the following. Compute the p-value. If p is less than alpha, reject the null hypothesis. If p is greater than alpha, do not reject the null hypothesis. If p is less than or equal to alpha, we say that the null hypothesis is rejected at the alpha level, or that the result is statistically significant at the alpha level. Example 3. Suppose we found the p-value that was equal to 0.0122. Do we reject the null hypothesis at the 0.5 alpha level? Do we reject the null hypothesis for alpha at the 0.01 level? For the first one, because p is less than or equal to 0.05, we reject the null hypothesis at alpha equals 0.05 level. For the second one, because the p-value was greater than 0.01, we do not reject the null hypothesis at the alpha equals 0.01 level. Example 4. The mean height of an adult man in the United States is 69.7 inches, with a standard deviation of 3 inches. A sociologist believes that taller men may be more likely to be promoted to positions of leadership. The mean height mu of male business executives may be greater than the mean height of the entire male population. A simple random sample of 100 male business executives has a mean height of 69.9 inches. Assume that the standard deviation of the male executives is 3 inches. Can we conclude that male business executives are taller on average than the general male population at the alpha equaling 0.05 level? We first check the assumptions. We have a simple random sample, check, and the sample size is larger than 30, check. The assumptions are satisfied. The null and alternative hypothesis are, so the null is that mu is equal to 69.7, and the alternative is mu is greater than 69.7. Because the assumptions are satisfied, the sample mean is approximately normally distributed with the null hypothesis 69.7, and the standard deviation is 3 over the square root of 100, which is equal to 0.3. The test statistic is 69.9 minus 69.7 over 0.3, which gives us 0.67. Since this is a right-tailed test, the p-value is the area to the right of z equaling 0.67. Using table A2, we find the area to the right of z equaling 0.67 to be 0.2514. The p-value of 0.2514 is not unusual. Since p is greater than 0.05, we do not reject the null hypothesis at the alpha equals 0.05 level. Thus, what does that mean? There is not enough evidence to conclude that male executives have a greater mean height than adult males in general. The mean height of male executives may be the same as the mean height of adult males in general. Example 5. At a large company, the attitudes of workers are regularly measured with a standardized test. The score on the test range from 0 to 100, with higher scores indicating greater satisfaction with their job. The mean score over all of the company's employees was 74, with a standard deviation of 8. Some time ago, the company adopted a policy of telecommuting. Under this policy, workers could spend 1 day a week working from home. After the policy had been in place for some time, a random sample of 80 workers was given a test to see if their mean level of satisfaction had changed since the policy was put into effect. The sample mean was 76. Assume the standard deviation is still 8, and we conclude that the mean level of satisfaction is different since the policy changed at the alpha equals 0.05 level. We first check the assumptions. We have a simple random sample, check, and the sample size is large, greater than 30, check. The assumptions are satisfied. The null and alternative hypothesis are mu is equal to 74 and mu is not equal to 74. Because it said changed. It didn't tell us higher or lower. It just wanted to know if the satisfaction had changed. Because the assumptions are satisfied, the sample mean is approximately normally distributed with the mean equaling 74 and the standard deviation equaling 8 divided by the square root of 80, which is equal to 0.8944. We now compute the test statistic, which is 76 minus 74 over 0.8944, which equals 2.24. Since this is a two-tailed test, the p-value is the sum of the area to the right of z equaling 2.24 and to the left of z equaling negative 2.24. Using table A2, we find the sum of these areas to be equal to 0.0250. So we can see from this graph how half of the area was to the left, half of it's to the right. When we sum it up together, we get that 0.0250. So since P is less than or equal to 0.05, we reject the null hypothesis at the alpha equaling 0.05 level. So what does that mean? We conclude that the mean score among employees has changed since the adoption of telecommuting. So that's what's really important with these hypothesis tests is that last statement. You do all this math, but what does that math mean? In this case, we're saying, yes, we can confirm that the mean score of employee satisfaction has changed. So that's what's really important here, getting all the math to be able to make that final conclusion. In the previous example, we rejected the null hypothesis that mu equals 74 at alpha equals 0.05. In doing so, we are saying that 74 is not a plausible value for the population mean. Another way to express information about the population mean is through a confidence interval. If we construct a 95% confidence interval for the population mean about the attitude of workers, we find the interval to be 74.247 is less than mu, which is less than 77.753. We note that this interval does not contain the null hypothesis value of 74. The confidence interval for mu contains all plausible values for mu. Because 74 is not in the confidence interval, 74 is not a plausible value. Recall that a type 1 error occurs if we reject the null hypothesis when it is true, and a type 2 error occurs if we do not reject the null hypothesis when it is false. We would like to make the probabilities of these errors small. The probability of a type 1 error is equal to the significance level, which is denoted by alpha. In other words, if we perform a test at a significance level of alpha equals 0.05, the probability of making a type 1 error is 0.05, or we have a 5% chance of making a type 1 error. Because alpha is the probability of a type 1 error, why don't we always choose a very small value for alpha? The reason is because the smaller a value we choose for alpha, the larger the value of beta, the probability of making a type 2 error. So there's a trade-off here. Sometimes people report only that a test result was statistically significant at a certain level without giving the p-value. It is much better to report the p-value along with the decision whether to reject or not. There are two reasons for this. There's a big difference between a p-value that is just barely small enough to reject and one that is extremely small. For example, at the 0.05 significance level, there's a huge difference between a p-value of 0.049, which is almost right at that significance level, so it's really close, and a p-value of 0.0001. Not everyone may agree with your choice of a significance level alpha. By reporting the p-value, we let people decide for themselves at what level to reject the null hypothesis. When using the critical value method, you should report the value of the test statistic rather than simply stating whether the test statistic was in the rejection region. This will tell the reader whether the value of the test statistic was just barely inside the critical region or well inside. Very similar to the p-value, you're just letting the reader know, is it really close, or is there no question that we should reject? Also, it provides the reader with an opportunity to choose a different critical value and determine whether the null hypothesis can be rejected at that different level. When a result has a small p-value, we say it is statistically significant. It is therefore tempting to think that statistically significant results must always be important. Sometimes statistically significant results do not have any practical importance or practical significance. For example, a new study program may raise student scores by 2 points on a 100-point scale. This improvement may have statistical significance, but is the improvement important enough to offset the cost of training teachers and the time invested on behalf of the students? This program was really expensive, time-consuming to implement for all the teachers, and it's only going to raise the student scores by 2 points. Well, it might be statistically significant. The numbers do say, yes, there's something here. It may not be practical to implement it because of the large cost and the time to do it. So that's just an example of practical significance versus statistical significance.